These videos are addressing the topic of machine vision, where we're trying to do object identification. In other words, the field of view of the camera has captured a scene with a number of different objects in the scene, and we want to figure out what these objects are. Object identification is an ongoing area of machine vision research. So in these videos, I'll only be able to show you one approach for how to do this. And you should understand that this one approach does not always work, but this approach will give you a place to start from when you need to do the object identification task, and it should also give you enough of a background that you will be able to read the current research in machine vision object identification and understand what the different approaches are that the researchers are taking. The task of object identification consists of two distinct steps. The first step is called image segmentation, and that's the topic that we're going to be talking about in the videos today. In the second set of videos in this series, we'll be talking about identification by features, the second step in the process of object identification. Today's set of videos will be about image segmentation, the first of the two tasks within object identification. Image segmentation is the task where we're trying to split up an image into the individual objects contained within that image. For example, I'm showing here a picture that I pulled off of a website showing a street scene. If we apply image segmentation to this image, we might be able to identify that there is an object right here, and that there is another object right here. We might have a reason to want to be able to tell that the first object is some sort of a garbage can of some sort, and the other image is a person. If we want to be able to do that, the first step is to be able to split up this image to identify that this is an object and this is an object. And this process is what's known as image segmentation. In image segmentation, we start off with an image. The image is a matrix that has one number representing each pixel in the image. There are 3 of these matrices stacked on top of each other, so that each matrix represents one of the 3 colors red, green, and blue. The value of each element in the matrix can range between 0 and 255, where 0 represents complete darkness and 255 represents complete lightness or brightness. In image segmentation, we want to process this image to transform it into a different matrix. We will call this other matrix the object matrix. The object matrix has the same number of rows and columns as the original image matrix, but it does not have 3 of these matrices stacked on top of each other. It only has one matrix. The value in each cell of this matrix is an object label number, where all pixels that belong to a single object have the same label number. For example, let's suppose that our original image was a picture of several red squares. I've shown here 3 red squares in our original image. If we took a picture of these 3 red squares, the image matrix would have the first matrix representing the red color. It would have high values near 255 in these pixel locations where the red squares are, and the green and blue matrices would have low values in the locations of the red squares. We want our object matrix to recognize that these three squares are individual objects and that these three objects are different from the white pixels surrounding them. The output that we would like for our object matrix would call all of these white pixels object number 1. And so the output, the desirable output, would be to have a number 1 in all of the pixels that correspond to the white pixels in our image. Next, we want to pick up these three red squares as different individual objects. So we want our object matrix to have a different number, say 2, in all of the pixels corresponding to the first red square. It would then place a 3 in all of the pixels corresponding to the next square, and a number 4 in all of the pixels representing the third square. This is the target or desirable output of our image segmentation. This kind of an output will let us recognize that there are three distinct objects in this image, and we know where the borders of that object are, and we can do other kinds of operations on each of these objects. For example, we could figure out how many pixels each of the objects takes up, or how tall the object is, or how wide. Image segmentation is the process by which we go from the image to the object matrix. And I'm now going to give you an algorithm that will allow us to do this particular transformation. Let's now take a look at the image segmentation process. The image segmentation process consists of 4 steps, where the 4th step is to apply the object labeling algorithm. The first 3 steps have to do with conditioning the image to be ready to apply the object labeling algorithm. Let's take a look at the first 3 steps that have to do with conditioning the original image. Step 1 is to convert the color image to a grayscale image. We learned several ways to do this in Robotics 1. One way to do this is to isolate a single color. Remember that the way we did this was we took the matrix corresponding to one of the 3 colors, red, green, or blue, and we subtracted the other 2 colors. For example, if we want an image that only has the red colors, we can take the red matrix and subtract the green and blue matrices. Another way to do this is to combine colors. In this approach, we have the grayscale image equal to some constant times the red image plus some constant times the green image plus some constant times the blue image. And we want these 3 constants to all add up to 1 so that the resulting grayscale image has pixels that range from 0 to 255, just like each of the individual color matrices range between 0 and 255. I won't go into any more detail on this because we did this in detail in Robotics 1. If you don't remember this, please come and ask me about it. Step 2 in the image segmentation process is to convert the grayscale image to a black and white or binary image. In a black and white or binary image, each pixel in the image does not range between 0 and 255. Instead, each pixel has either a 0 or a 1, representing whether that pixel should be white or black. The typical method to do this is the threshold method. In the threshold method, we say that any pixel that is greater than a threshold, or in some cases we might say if a pixel is less than a threshold, then the pixel will be equal to 1. Otherwise, the pixel will be equal to 0. This threshold is a value between 0 and 255. For example, we might say if a pixel is greater than 100, then the output pixel should be 1, otherwise the output pixel should be 0. This step allows you to go from an image with pixels varying from 0 to 255 to an image with pixels that have values only 0 or 1. And this will give you a black-white or binary image. Step 3 in the image segmentation process is to apply transforms if necessary. Our goal in pre-processing the image to get a black and white image is to have each of the objects that we want to identify separated from one another. For example, if there are two squares that we're trying to identify as objects in our image, we would like the two objects, the two squares, to be separated from one another in our black and white image, sort of as I've shown here. These two black images are separated from one another with a space of white in between. This is what we want to have. Sometimes we end up with a black and white image where the objects are not separated from one another, but they touch one another slightly. For example, we might end up with an image that looks like this image that I'm drawing on the side here. Here we have two black images and we want to identify both of these objects. However, the two objects are not separated from one another, they're touching. If we have a case like this, these two objects will not be picked up as separate objects, they'll be picked up as one single object. One way to deal with this is to do this step 3, apply transforms. Some transforms that we have available to us are called opening and closing. We won't go into the opening and closing algorithms in this class, but MATLAB and some other image processing programs have opening and closing algorithms predefined. In short, opening and closing algorithms cause objects to become either shrunken or expanded. An opening algorithm will cause each of these squares to become smaller, and so since both of these squares will shrink, that will cause them to no longer touch each other and they'll be separated. A closing algorithm is good when a single object has been broken up into pieces. For example, perhaps you want to identify a square, but the square has pixels that are left white after you've converted to black and white. For example, perhaps your single square that you want to identify as a single object looks like the image that I'm drawing right here, with some white pixels in the center that you don't want to be there. In this case, you can use a closing algorithm to make each of the individual pieces of this square become expanded in order to close the gap that's inside the object. The opening algorithm is useful for this case over here, where we want to separate two objects that are touching. Once we have a black and white image with each of our individual objects separated from one another, we're ready to move on to step 4, which is to apply the object labeling algorithm. The object labeling algorithm is an algorithm that takes us from a black-white image to an object matrix. The black-white image and the object matrix have the same dimensions. The black-white image is populated with 1s and 0s representing black and white regions. I've shown here a very low resolution example where we have 2 objects represented by groups of 1 pixels and 1 object represented by a group of 0 pixels. Here's how the object labeling algorithm works. We're going to start by keeping track of the highest label number. At the beginning of the algorithm, the highest label number is 1. We will start by filling in the first row and the first column of the object matrix. We start by placing the highest label number, 1, in the upper left-hand corner of the object matrix. Now, we will step through the first row of the object matrix. If the black-white image pixel in the object matrix pixel that we're trying to fill in is the same value as the black-white image pixel to the left of it, then the label number should be the same. I'm going to write this rule like this. If the black-white matrix element row I, column J, is equal to the black-white element row I, column J minus 1, then the object matrix element row I, column J, is equal to the object matrix element row I, column J minus 1. Another way to say this is that if the black-white image value in the current pixel is the same as the black-white image value in the last pixel, or the pixel to the left, then the object matrix value should be the same. So in this case, the black-white image value in the pixel to the left is 1, and the black-white image pixel value in the current pixel is also 1, and so the label should be the same. It also gets a 1. The next pixel has a black-white image value of 0, but the previous pixel has a value of 1. So those values are not the same, and so I will place the next label value. And I'll increment the label number. So down in my rule here, I'll say else object matrix IJ equals label number plus 1. In my next pixel, I see that the black-white image value is 1 and the previous value was 0, so once again I use the next label number and I increment my maximum label number. Now that we've finished with the first row, we'll move on to the first column of the object matrix. The rule for the first column of the object matrix is the same as the rule for the first row of the object matrix. The only difference is that we're looking at the difference in rows instead of the difference in columns. So if the black-white element IJ is equal to the black-white element I minus 1, that's the last row, column J, then the object matrix row I, column J, is equal to the object matrix row I minus 1, column J. Else, the object matrix number in row I, column J, should be equal to the next label number. So in my object matrix, I go to the next element in the first column, and I see that the black-white image value is the same as the last black-white image value in the last row. Because these values are the same, the object matrix value should be the same also. Next, I see that the black-white image value in the next row is different than the black-white image value in the last row. So, I have to place the next label number and increment my label. You can see here that there's already been a labeling mistake made. The black-white image values are the same in all of these pixels, so the label for all of these pixels should be the same. However, in our object matrix, we've placed a 2 up here, and we've placed a 4 down here. However, in the next steps in this algorithm, we will see this mistake corrected. Once we've finished the first row and the first column of the object matrix, we can fill in all the rest of the pixels. There are 3 rules that we use to fill in all of the rest of the pixels, and we have to apply all 3 of these rules to every pixel. Rule number 1 looks like this. For all of these rules, we're going to assume that we are trying to fill in the object matrix is this pixel, the one in the lower right. And I've shown you here a 2 by 2 segment of pixels because this 2 by 2 segment of pixels is the group that we want to look at in order to obey these 3 rules. In other words, whichever pixel we're trying to fill in, we'll look at the 3 pixels that are adjacent to it, to the top and to the left. Rule number 1 works like this. If the black-white value in the pixel to the left of the pixel we're trying to fill in is equal to the black-white value of the pixel we're trying to fill in, then we should take the object matrix value in the pixel to the left and duplicate that value in the pixel to the right. In other words, if the black-white value is the same in the 2 adjacent pixels, the pixel we're trying to fill in and the pixel to its left, then the object matrix value should be the same also. Rule number 2 is somewhat more complicated, but it will end up making our object matrix much more accurate. Rule 2 works like this. If the black-white image pixel value to the left of the pixel we're trying to fill in is equal to the black-white value of the pixel to the top, and equal to the black-white value of the pixel we're trying to fill in, but the object matrix value is not the same in these 3 pixels, then we choose the smallest label number in all 3 of the pixels and assign that label number to the object matrix of all 3. The last rule addresses the case where the black-white values are the same in a column, and it works like this. If the black-white value in the pixel to the left is not the same as the black-white value in the pixel, but the black-white value in the pixel to the top does equal the black-white value in the pixel, then the object matrix value in the pixel should be equal to the object matrix value in the pixel to the top. Let's now look back at our example and fill in the rest of the object matrix pixel values using these three rules. Here's what we had after filling in the first row and the first column of our object matrix. We now want to fill in the other elements of the object matrix, and we have to use the three rules. Let's start by trying to fill in this pixel here. In order to do that, we're going to use the group of pixels that includes all of the pixels to the top and left of that pixel to make a group of 4. So we'll look at this group of 4 pixels here and this group of 4 pixels here. The first rule says that if the black-white image value to the left of our pixel is the same as the black-white value in the pixel, then the label should be the same. So I will start by putting the same label, which in this case is 1, in our object matrix. We have to then check for our second rule, which says that if the black-white image value here is the same as the black-white value here, which it is, but the object matrix value here is not the same as the matrix value here, then we have to do something different. But in this case, the object matrix value here is the same as the value here, so we're good to go. We can leave the value 1 where it is. The third rule says that if the BW value here is the same as the BW value here, then the object matrix value should be the same, and they are. So we've satisfied all three rules. We can leave the value 1 in this pixel. Let's go on to the next pixel. We're going to try and fill in this pixel. So to do that, we'll have to look at this group of 4 pixels here, which corresponds to this group of 4 pixels here in the black-white image. Rule number 1 says that if the black-white value here is the same as the value here, then the object matrix value should be the same also. In this case, it's not the same, so we're not going to fill in that pixel value. Rule number 2 says that if the BW value here is the same as the BW value here and here, but the object matrix value is different, then we have to do something different. But here the BW value here is different than the value here, so rule 2 does not apply. Rule number 3 says that if the BW value here is the same as the value here, then the object matrix values should be the same. That rule does apply because the BW value here is indeed the same as the value here. So according to rule 3, we have to take the object matrix value here and apply it here. And so we get a 2 filled in right there. Next we move on to this pixel. So we're going to look at this group of 4 pixels. Right there and right there. Rule number 1 says that if the BW value here is equal to the value here, then the label should be the same. So that rule does not apply to this group of pixels. Rule number 2 says that if the BW value here is the same as here, then the label has to be the same. So that rule also does not apply. Rule number 3 says that if the BW value here is the same as here, then the label should be the same. So that rule does apply. I go and get the label for this pixel and I apply it down here. And we move on to this pixel. So we're going to look at this group of 4 pixels, there and there. Rule number 1 says that if the BW value here is the same as here, then the label should be the same. Rule number 2 says that if the BW value here and here are the same, then I have to make the labels the same. So that rule does not apply. Nor does the third rule, which looks for a same BW value here and here. So that pixel is finished. Next, we'll move on to this pixel. Rule number 1 says that if the value here is the same as the value here, I have to use the same label. Rule number 2 says that if the BW value here and here and here are the same, then I take the smallest label number and apply it to all 3 pixels. In this case, this rule does apply. The BW value in all of these pixels is the same, but the label number is not the same. This rule tells me that in this case, I take the lowest label number of these 3 pixels, which in this case is 2, and I have to apply it to all of these pixels. So this label will become 2, and so will this one. Finally, I look at the last pixel. Rule number 1 says that if the BW value here is the same as here, the label should be the same. So that rule does not apply. Rule 2 says that if the BW value here is the same as here and here, then the label should also be the same. And that rule also does not apply. Finally, the last rule says that if the label or the BW value here is the same as here, then that label should be the same. So that rule does apply, and this pixel gets a 3. And this is our final object matrix. You'll notice that this object matrix is not perfect. We've still made an error down here in the lower left-hand corner. Sometimes errors like this can be fixed by going back through the object matrix to make sure that all of the rules are satisfied. And sometimes errors remain even when all of the rules are satisfied. Often this tends to happen in the first row or the first column, where we do not have a full set of pixels to the top and to the left that we can use to apply the rules. So this object labeling approach is good and it works in most cases, but it is not error-free. Does not work all the time. But it's a simple method that is easy to apply and works in most cases, and so it's a popular algorithm to use. Once we're finished with the object labeling algorithm, we can determine all different kinds of things about the objects in our image. We can tell how many objects there are by looking at the maximum value in the object matrix. We can also tell things like the size of the objects in our image. In the next set of videos for the next class, we'll look at how we can use information in the object matrix to determine some things about what these objects actually are. What is the identity of the objects? For now, we're going to stop at the point where we've obtained the object matrix, identifying the locations of the objects in the image.